this lecture we will talk about the so-called small gain theorem, which is a very nice application of L stability that we have recently introduced, and in particular it's a useful tool in analyzing and studying systems in feedback connection. Okay, so what we will do in this lecture is we're going to consider two systems which we independently know the L stability properties of. Okay, we're going to call one of those systems H1, and then the other system is H2. Okay, so we know the L stability properties of H1 and H2, suppose. And what's being done is we construct an aggregate system, okay, a larger system, by connecting H1 and H2 in feedback form. Okay. And this is what we have. So H1 block represents our first subsystem with input E1, E for error, and Y1 as its output. And H2 block represents our second subsystem with input E2, okay, and output Y2. And here U1 and U2, they represent the external inputs, or perhaps external disturbances to the overall system if they exist. Okay, now we're going to make certain assumptions regarding this connection in our systems, okay, and then in the light of those assumptions we will state and then prove the small gain theorem. So we're making two assumptions, okay, that is, we assume two conditions are satisfied. One of them is feedback connection is well defined. Okay, so we don't want things like the algebraic loops. If you have some experience with simulating, every once in a while one makes a mistake in the MATLAB, gives you the warning that there's some algebraic loop somewhere, which means that the feedback connection is not well defined. Okay, so we're assuming that the feedback connection is without any problem. Okay, by which we mean for each pair of input signals, U1 and U2, the signals E1, E2, Y1, Y2, which depend on the inputs U1 and U2, and also the initial conditions of our subsystems, if our subsystems are dynamic. Okay. And we assume that those signals of interest always and uniquely exist. Okay, that's our first condition. Second condition has to do with the L stability properties of our subsystems H1 and H2. We're assuming that those systems are finite gain L stable. Okay. So both H1 and H2 finite gain L stable. indicate whether that's L2 stable, whether they're L2 stable or L stable. Because well, we don't care. All we care about is that by L stability we mean the same L stability for both subsystems. Okay, so both are, let's say, L2 stable with finite gain, or both are L infinity stable with finite gain. That is there exists are finite gains, gamma 1 and gamma 2, and y1 less than or equal to gamma 1 times the input to the first block, and input to the first block is denoted by E1. And if you remember the definition of L stability, we have an additional constant term which represents the effects of the initial conditions. Okay. And this depends on, it changes from initial condition to initial condition. And likewise for the second subsystem, we have a similar relation between its output and its input. Its output is y2 and its input is E2 plus the initial condition term, beta 2. Okay. Where beta 1, beta 2 are determined by the initial conditions x10 and x20, if you will, of the systems. Okay, now what we're going to do is we're going to consider this connection as a single system with inputs, or the input u1 and u2 considered together as a single vector. And we have two ways to look at the situation from the output point of view. We could either take the outputs to be these error signals, E1 and E2, considered together as a single error signal, or Y1 and Y2. Okay? Regardless of what output you choose, the theorem, the statement of the theorem, remains valid. Okay? So let's be precise about what we mean there. Okay, now we can consider, and we will consider, the overall feedback connection is a single system whose input we take to be U, which we define as this vector, okay, U1 and U2. And the output of the system, the overall system, is either Y, okay, which we construct by concatenating the individual inputs, outputs of the subsystems, or the error signals, considered as a single signal, okay? A vector signal, E1 and E2. And having introduced our new notation, let H3 and H4 denote the overall systems from for two possibilities, either for the output taken as this or taken as this. Okay. So let H3 and H4 denote the corresponding systems. corresponding closed loop aggregate systems. Okay. H3 is the system that we, or H3 is our notation to denote the system whose input is U and the output is E, the error signal. Likewise, H4 is such that its input is U, same as H3, but this time we consider the output as Y. Okay. And staple theorem holds for both of these possibilities. Now, this is our small gain theorem. It's theorem 5.6 in the text. Under the conditions we listed, and which we call assumptions A1 and A2. A1 was that the feedback connection is well defined. The signals always exist for all inputs and for all initial conditions. And A2 was that both subsystems, H1 and H2, are L-stable with finite gain. And if that set of conditions hold, then both systems, both H3 and H4 are finite gain L-stable if, okay, so second assumption once again was that each individual system was finite gain L-stable with gains gamma 1 for H1 and gamma 2 for H2. And now the feedback connection turns out to be L-stable if the product of those individual gains, gamma 1 and gamma 2, is strictly less than unity. If gamma 1 times gamma 2 is strictly less than 1. Okay. Now I'm going to prove it, but before starting our proof, I want to emphasize that this is just a one-directional condition. That is, even if gamma 1 times gamma 2 is larger than 1, there may be some situations where the overall connection is still finite gain L-stable. Okay, so this is just a sufficient condition, but not a necessary condition. Okay, now under that sufficient condition, let's prove that we have finite gain L-stability for our feedback connection. And the proof is really simple. It's just a few lines of bookkeeping while remembering the definitions of L-stability. Okay. So we begin by writing how E1 is defined. E1 is U1 minus the output of the second subsystem. Okay, so that's from the feedback connection. And by the way, this is minus because conventionally we have negative feedback. But as far as this theorem is concerned, the sign of feedback is not really important. It could either be minus or plus. Likewise, for the other connection, we have plus. Okay, E2 is U2 plus Y1. And that could have, there you can replace a plus with a minus. Okay, so as far as this theorem is concerned, it doesn't really matter. Okay, so that implies by triangle inequality, the L norm of the signal E1 is less than or equal to L norm of U1 plus L norm of Y2. Okay. Because we'll be using this triangle inequality, that this the sign of this summation is not really important. That's what I meant. Okay. And that's less than or equal to u1 ln of u1 plus, okay, gamma 2 e2 l plus beta 2. Second system was finite gain unstable with gain gamma 2. Therefore, the output of the second system can be upper bounded by that finite gain times the L norm of the input of the second system, which is E2, plus the term that represents the effect of the initial conditions. Okay, so that's our first inequality, which we put in our pockets. And then we do the same thing for E2. E2 equals U2 plus Y1. And then we can write, as we did here, L norm of E2 less than or equal to L norm of U2 plus L norm of Y1. Okay, just the triangle inequality that we know from norms. And then that's less than or equal to L norm of U2. And then, since the first subsystem is finite gain L stable with gain gamma 1, this term we can upper by gamma 1 times the input to the first subsystem, which is E1, plus the term that represents the initial conditions. Okay, gamma 1, L norm of E1, plus the constant, which we're calling beta 1. That's our second inequality. Okay, now let's combine those two inequalities. Obtain an upper bound on the signals E1, or the norms of signals E1, E2 in terms of the norms of the inputs U1 and U2. So combining 1 and 2 yields, okay, L norm of E1 less than or equal to L norm of U1, okay, and then instead of this term here, which upper bounds L norm of E1, we can use the second inequality and upper bound that by this term here. So therefore we have L norm of E1 is less than or equal to this guy plus this guy plus gamma 1 times L norm of, again, E1 itself plus beta 1. Okay. Right. Plus, okay, gamma 2 times what upper bounds this term, which is here, L norm of U2 plus gamma 1 E1 plus beta 1. Okay, and we have this term, so let's also put it here, beta 2. So what we have done is, using those two inequalities, we have constructed an upper bound on the norm of E1. On the right hand side, we have, so this should be E1. Okay, we have another E1 term, so what we do is, now we're going to collect the E1 terms on one side, on the left hand side. If you do that, you have before that, let's rewrite this. U1 L1 plus gamma 2 U2 plus gamma 1 gamma 2 E1 plus gamma 2 beta 1 plus beta 2. And then we take this guy to the other side and write 1 minus gamma 1 gamma 2 less than or equal to what remains, which is L plus plus gamma 2 L plus the constant terms. Okay. Therefore, we can write, or we can divide both sides with 1 minus gamma 1 gamma 2, and that operation will not change the direction of this inequality, because gamma 1 minus gamma 2 is strictly less than 1. Therefore, this thing here is positive. Less than or equal to 1 over 1 minus gamma 1 gamma 2. Plus the constant terms 1 minus gamma 1 gamma 2. So this is our inequality 3. Okay? So what we obtain is we obtain upper bound on the first output, okay, E1, and now we're considering the H3 system for which the output is denoted by E, and E is the signal that we obtain by concatenating E1 and E2 and constructing a single vector. Okay, so the first output variable is upper bounded by this term, where we have on the right hand side the norms of the inputs U1 and U2. We can do the same thing, or a similar thing, for the other output, that is E2. And we can write, due to symmetry, 1 minus gamma 1 gamma 2. Okay, now we swap the indices, gamma 1 U1 L plus gamma 1 beta 2 plus beta 1 minus gamma 2 gamma 1. Okay. And let's call this inequality 4. And basically, we're almost done. What we're going to do now is, using those two inequalities, we're going to obtain a relation between the L norm of our output signal E, which is E1 and E2, considered together as a single vector. Okay, and we're going to figure out the relation of this, the L norm of the E, which is our output in this case, to the L norm of the input U. U is U1 and U2 considered together as a single vector. And it's very easy. All we have to do is remember some very basic properties of norms, and then the result will follow effortlessly. Okay. Now, we have to make some simple observations, and let's make them. Note that the L norm of E, which is the L norm of this vector signal, E1, E2, because by definition, E is this vector, E1 and E2. Okay. And by triangle inequality, this is E1, 0, L, plus 0, E2, okay, L. And this thing here is the norm of this vector, the same as the norm of its non-zero component, which is E1. Therefore, we can write E1 L, and likewise for this guy, E2. Okay, so that was our first observation. Norm of E is less than or equal to sum of individual norms of its constituents. And then also max and U was defined as U1 and U2, that vector, and then the maximum of the individual L norms of the components of U can and that will be larger than the atom of u. That's also that's also easy to see. Now, using those two observations and the inequalities that we obtained, 3 and 4, we will be able to write down the final inequality, which will give us the answer. Okay, hence 3 and 4, or more precisely, 3 plus 4, okay, 3 is here, 4 is here, will give us norm of E less than or equal to 1 plus gamma 1 plus 1 plus gamma 2, that leaves 2 plus gamma 1 plus gamma 2. 1 minus gamma 1 gamma 2 times the atom of the input u plus we add up all the constant terms that appear on the very right. Gamma 2, beta 1 plus gamma 1, beta 2 plus beta 1 plus beta 2 over 1 minus gamma 1 gamma 2. Okay. And by the very definition of alpha stability, we see that the system H3, whose input is U and output is E, is finite gain, alpha stable, with gain no larger than the term that appears here. So let's call this gamma 0. Okay, so we're defining it. Okay, let's define this as gamma 0, and let's define this as the constant term beta 0, which presents the effect of initial conditions. Okay, therefore, system H3, the overall system that we obtain by considering feedback connection as a single system, is finite gain alpha stable. Okay, with gain no larger than gamma 0. Okay. Likewise, the H4 system, for which the input is still U, but this time the output is Y, can be shown to be finite gain alpha stable in a very similar way. So we have proven the statement of the theorem. Okay, so that's the end. Okay. Now let's apply this useful tool, useful in analyzing the stability properties from the input-output point of view of feedback connections, on a simple example that we're familiar with from circuit theory. We have the series RLC. Okay, connection. This one port. That one port is part of another circuit, and that circuit can be represented by, let's say, the following dependent source. Dependent voltage source. Okay, plus minus. Let's call this current Y, and the voltage that's produced by this dependent source is a function of Y in the following way: Y times cosine Y. Okay. Clearly, the relation from the input of this block to its output is nonlinear. Then we have the linear components for the reservoir elements R, L, and C indicate the resistance, inductance, and capacitance of our LTI elements. The condition is, or the problem is the following: find conditions on system parameters RLC. We're talking about passive components, they're all positive, so that heat dissipated on the resistor is finite. What's heat dissipated over the resistor? It's the energy that's consumed by the resistor from time 0 to the end of time, infinity, and that the energy is equal of the power dissipated on instantaneous power dissipated on the resistor at any given time, and the power is voltage times the current of the resistor, or simply resistance times the current squared. And what we want is to find conditions on the circuit parameters so that this integral, okay, we're integrating the power of the resistor, so therefore that's the energy that's absorbed by the resistor, absorbed and given out to the environment as heat, and we want this to be less than infinity. Okay. This being finite means that y of t is converging to 0. Therefore, everything this circuit is, in a sense, converging to the origin. Okay, so in a sense, we're trying to figure out the stability of this input-free system. Even though it's input-free, it can be considered in a feedback connection. And when you do that, you consider it as a connection of two separate individual systems in feedback connection. Then you can use the theorem that we have just proven, the small gain theorem. We're going to do that, and we're going to find, using that theorem, some conditions on our system parameters so that the closed system is well behaved. Okay. So here is the solution. Now let us consider this one port, okay, series RLC LC circuit as our first subsystem, okay. And what are the input and the output? The input we take to be E, this voltage, and output is the current generated by that voltage. And then, since this is a linear system, the input output satisfy a relation that can be described by a transfer function. And that transfer function, P of S, is Y of S over E of S. Okay, Y is the current, E is the voltage. Therefore, we're talking about current over voltage, that is the admittance. Okay. So that equals 1 over R plus LS plus 1 over CS. Okay, so 1 over the impedance over this one port. And that is equal to 1 over LS squared plus R over LS plus 1 over LC. Okay, so that's the transfer function from the voltage at the port terminals to the current generated by that voltage. Now, we're going to consider this circuit as a connection of two subsystems. This is our first subsystem. The other subsystem is this, that's represented by that dependent source. Okay, so now the original circuit be seen as the following block diagram. Elements the following. Okay, we have here the transfer function that we have just computed. The input to that transfer function, or that subsystem, is the voltage that appears here, E, and the output is the current, which we're calling Y. Let's call this subsystem H1. Okay. Then we have here the other subsystem, which takes the output of the first subsystem as its input. Okay, so for which Y is the input and the voltage, Y cosine Y is the output. So this is the mapping Y to Y cosine Y. Okay, it is Y, and what it generates is Y cosine Y. So what it then generates is no other than this voltage, and with that voltage we're calling E. That's the input to our first subsystem. Okay. Then we can also consider an external input to the system, and what we have is this. Okay. Now, of course, in this case, in the nominal case, this external input, we don't have any external input, so we can simply take U to be 0, and then we can forget about that. What happens is we have an H1. What it does, it takes the voltage that's generated by the second subsystem as its input. It produces the current output, and that current acts as an input to the second subsystem. Second system produces the voltage, that voltage is the input, and so on. Okay, so we have this loop, we have that feedback connection. And then we're going to figure out, by using small gate theorem, whether this connection is well behaved in the sense that you start from arbitrary initial conditions, then you look at the signals and whether those signals remain bounded or not. Okay, so this is our LTI system, and it's dynamic, that is, the output not only depends on the input but also the initial conditions. As for the second subsystem, it's not dynamic, it's just a static map, but it's non-linear. Okay, so that's non-linear feedback. Now we're going to figure out the result of this connection from the input-output stability point of view. Okay, so let's figure out, if we can, whether these subsystems are L-stable. Now this is the transfer function of a linear system, okay, and the linear system, because we're talking about with passive components, RLC, is an exponentially stable linear system. And when that's the case, you can simply look at the transfer function, or the values of the transfer function on the imaginary axis to figure out its L2 gain. Okay, that was one of our theorems that we have seen recently. Okay, in particular, we can say gamma 1 is sub omega GJ omega. Okay, so you look at the magnitude Boyle plot and you figure out the peak magnitude, okay, and that the value that it takes at that peak is what we call it the L2 gain. Okay, so that was one of our previous theorems, and that is something that we can easily compute, and it appears at the so-called resonant frequency, which is 1/square root of LC radians per second, and the value is 1/r. Therefore, H1 is finite gain L2 stable with gain 1 over R, or the conductance of the resistor. How about gamma 2? That is, whether this is finite time L2 stable. Also, if it is, what's its gain? Okay. Since it's a static map, it's not that difficult to see what the gain is. Okay, so let's sketch the input versus output for this block or for that map. Note that the output is y times this cosine y. Cosine y does oscillate, but it has one nice property, and that property is that it's always, the magnitude is never larger than 1. Okay? Therefore, what we have is the output always remains within this envelope. Here the slope is 1, here the slope is -1. This is the origin, and y cosine y is something like this. It always remains within this sector, okay, with slope 1 and slope -1. So it's easy now to see that y cosine y, or its magnitude, is never larger than the magnitude of the input. Therefore, this inequality directly tells us the gain of L stability. In other words, gamma 2 equals 1. Okay. And its the second subsystem, H2, is finite gain L2 stable with gain equals 1. Okay? And now we have everything we need for small gain theorem. We have two subsystems connected in the feedback form. Both are finite gain L2 stable, and we know the gains. The gain of the second one is 1, and the gain of the first one depends only on the value of the resistance, 1 over R. And what we want is we want the overall system to be finite gain L stable, because that would imply that the power dissipated on the resistor is finite, and for that all we have to do is multiply those two guys, gamma 1 and gamma 2, and that should be less than 1, less than unity. Okay. So that means R must be larger than 1. Now, for resistance greater than 1, and the condition clearly does not depend on inductance or capacitance values, it only depends on the resistance of the resistor. We have the product of the individual gains less than 1, and closed loop system is L2 stable. Okay, so that's by small gain theorem. Then let's interpret the implication of L2 stability of the feedback system. So what we have is Y L2 less than or equal to gamma 0 U L2 plus the constant representing the initial conditions. Now in our case, we consider 0 external input. Therefore, here the norm of u is 0. Therefore, this term is 0. Okay. That would imply that L2 norm of y is less than or equal to 2 at all times, some constant, and that constant depends on the initial conditions. But nevertheless, once the initial conditions are fixed, that is, once the initial capacitor voltage and initial inductor current are fixed, then the L2 norm of the output is always less than some fixed constant beta 0. So that implies that, if you remember, the definition of L2 norm, what we're doing is I square dt, and then we take the square root. Okay, and that's less than or equal to what? Beta 0. So that's the definition of L2 norm. If that's the case, clearly what we can do is we can square both sides of the inequality. And here we have beta 0 squared. Therefore, this is less than beta 0 squared. And then we can multiply both sides with the positive constant r. And then if you do that, r times y squared dt is, this is the power of the resistor, and then this is the overall heat dissipated on the resistor from 0 to infinity. And that's less than or equal to this constant times that constant squared. In other words, it's finite. Okay, and that was what we were trying to show.